So far in the first section, machine learning, which is about linear regression, we have taught you that in supervised machine learning there is a data set D, which is a set of m data points, xi and yi, where I goes from 1 to n, where each of the xi is some k-dimensional real vector, and each of the yi's is some real scalar. Right. And we learn a functional mapping, so we consider a linear model. The function is a class of linear models. Where Fw of x is simply W transpose times xi, and we also discussed that this is perhaps not a good choice for functional mapping. Instead of mapping the function from x to y, we instead map it from some feature function to y. And we discussed that this phi is a feature function or a basis function that takes an input and maps it to some n-dimensional real space. So phi is a mapping from k-dimensional real vector to an n-dimensional real vector, right? And W is n-dimensional real vector, right? And we also showed you like how to compute the optimal parameter W star, both using closed form solution and also using the stochastic gradient descent. So this is what we have covered so far, and today we are going to give you a probabilistic interpretation of what we have done. We also assume that our loss function was an L2 norm. Sorry, I forgot the parameterization. So we discussed the loss function was simply L2 norm squared, which is so r equal to 1 to n yi minus 5 psi transpose times W square, right? So today we are going to give you a probabilistic interpretation of all of this as to like what's the probability, what's the probabilistic backend to doing all this, like the least square cost function, the linear models. So let's begin with understanding from probabilistic point of view.